what we don't know is how they get their masses, essentially.
Yeah.
And what's the hypothesis around as to why they might have their masses?
So I can tell you how we know they have masses.
Yeah.
Um, okay, I will draw this on this piece of paper, but eventually
We will digitize it afterwards.
We'll digitize it afterwards. But you basically have a situation where each neutrino is associated with another particle, okay, which is called a lepton. So an electron is the lightest one of these. An electron is charged, and so is the muon and the tau particle. And there are 3 neutrinos, one associated with each of them.
Okay.
When you have a particle physics process that occurs, so some interaction occurs, and you convert, in some sense, between these 2 states, between the neutrino state and the charged particle state, for example, you create neutrinos in what's called a flavor eigenbasis. So in one of the flavor eigenbases. And what that means is like, these are 3 different flavors here, 1, 2, and 3. And when a neutrino is born, it's born as one of them. Okay?
What do you mean by born?
When a neutrino just pops into existence from some other physical process.
Do we know how that process occurs or no?
Yeah, there are many processes that can emit neutrinos.
Okay.
So like in the same way that like you can have something hot emits like photons, like it glows red.
Or like these lights, I guess?
Or these lights, yeah. This is like a chemical process emitting photons. Yeah, so that's, that's an electromagnetic process.
Right.
So weak interaction processes can emit neutrinos.
Okay. And what are examples of weak processes? Forgot the middle word.
So, well, that's just anything that is mediated by those bosons you have on the table over there, which is a funny term to call them, but essentially they're these other particles called the W and Z bosons, and there's 3 of them. There's a charged W, so it has a positive and negative charge, and then you have the Z boson, which is like a neutral particle. These things are heavy, and when you construct like an interaction, but you still have to obey all the rest of the symmetries of the standard model, there are certain processes that are allowed to occur. So the case I'm thinking about is like when you convert between a neutron to a proton in a nucleus, like going back to our beta decay example. If you convert between a neutron to a proton, you have to conserve charge, so you have to also emit an electron. Because protons and electrons have opposite charges, and this has a charge of 0, the neutron has a charge of 0, and that's cool. Now, but you also have to conserve something else called lepton number, which is associated with these neutrinos. Because an electron is part of this lepton family, so you can't just have it show up out of existence, out of nowhere. So you also have to emit an anti-electron neutrino. So this is how an example of how a neutrino
Which is like
born.
antimatter, right?
Which is a version of antimatter, yeah.
Okay.
And this is an example of how a neutrino can be born. So now that it's born in this flavor state, this electron type. But as it moves through space and flying through space, you can detect it sometime later by the reverse of this process, for example. And when you do that, you either emit a muon, a tau, or an electron with some probability.
Some probability.
Some probability, which we can calculate.
Is it random, or is there a specific number to it that's like consistently reoccurring?
It's random in like, it's consistently reoccurring as a function of energy and distance traveled. Okay. But it's not random in the sense that it's just some random probability. It's like, okay, the chances of it being an electron is 1/3 at this distance and this energy. But if you move slightly further, the chances of it being an electron is like 1/4. So the whole total probability sums to 1, or at least we hope so.
Okay.
Unless there are other types of neutrinos that we're unaware of.